Welcome to Materials Innovation Forum. I'm Rittika, and today we are exploring the critical transition from laboratory synthesis to industrial implementation of metal organic frameworks for gas separation and hydrogen storage application. Joining me today is Dr. Sibo Chetry, currently conducting postdoctoral research in Germany at the intersection of chemistry, material sciences, and sustainable energy. Dr. Chetri, MOFs represent one of the most structurally diverse material classes ever developed, yet industrial adoption remains limited. What fundamental challenges must be addressed to bridge this laboratory to market gap, do you think?
Yeah, first of all, thank you, Ritika, for this beautiful question and for the podcast as well. What I think is the primary challenge is what I can see is the performance scalability paradox. Marked with the exceptionally laboratory performance surface area exceeding 7,000 meters square per gram, precise molecular selectivity often rely on synthetic condition. Incompatibility with the industrial manufacturing, we are dealing with the material that require careful control crystallization condition, expensive organic linker, and post-synthetic modification that become economically prohibited at this scale. The question isn't whether MOF can outperform traditional adsorbents like zeolites, but whether they can do so at cost and production volume relevant to industrial gas process as well as can be adopted within the same existing system.
That was a really well rounded answer, but let's start by examining synthesis scalability specifically. So, what are the fundamental barriers to scaling MOF production from milligram laboratory quantities to industrial tonnage requirement?
Yeah, this is a very crucial question, and I think the scalability challenge operate at multiple levels. And crystallization kinetics that work in small volume, well mixed laboratory reactor often fail in large scale continuous process or in a pilot scale. Nucleation and the growth dynamic change dramatically with reactor geometry, mixing efficiency, and the heat transfer characteristics. Many high performing MOF require solvothermal conditions and elevated temperature, including pressures in or and that become economically and environmentally unsustainable at the industrial scale. And itself, the linker cost problem is equally significant. And advanced MOF often utilize custom design organic linker that cost thousands of dollars per kilogram in research quantities. For hydrogen storage application targeting DOI required of $10 kilowatt per hour system cost and linker cost alone can exceed economically viability by order of magnitudes.
Okay, so can you elaborate on or give us insights about how are researchers addressing these economic constraints at large?
Yeah, there are many. So several strategies are emerging, like linker simplification, focus on common commodities, chemicals as a building block, like terephthalic acid, ricemic acid, rather than exotic heterocyclic compounds, which need I don't know, 5 or 6 step to synthesize. Water-based synthesis eliminate the expensive organic solvent like a DMF, DMA, which are been commonly used for synthesizing these metal organic frameworks, while enabling continuous processing. Some approach utilize industrial waste stream as linker sources, converting plastic waste derived monomer like LTA or converting into terephthalic acid monomer into the MOF component, creating a circular economy approaches that improve economic while addressing the sustainability and also reducing the waste from the industrial. So I think this is what I really believe.
Okay. So, moving forward to specific applications, how do you think MOFs address current limitation in industrial gas separation processes?
If we talk about gas separation industrially, I mean, yeah, so MOFs are most commercially viable near-term applications. Like there are many for flue gas or maybe for natural gas, but the traditional separation process always include this cryogenic distillation for air separation or like pressure swing adsorption for hydrogen purifications are energy intensive and capital intensive. MOF enable more selective, lower energy separation through molecular recognition rather than purely a dynamic process. For example, for the flue gas separation, like a CO2 N2 separation from the cement factories, MOF like Calc20 has demonstrated a remarkable selectivity under humid conditions where the traditional has often failed. And the key insight is that the MOF selectivity can be tuned through precise pore control and the functionalization and creating material that discriminate between the molecule with minimum size or the polarity difference. Yeah.
Right. So, on this topic, what about the specific challenges of hydrogen purification, do you think?
Okay, hydrogen purification from syngas or reforming process, steam reforming, these are the basic methods or process from where the hydrogens are being generated and which require separating H2 from CO, carbon monoxide, carbon dioxide, methanes, and water component with similar kinetic diameter. I mean, H2 is smaller than the rest of them, but still they are close by, but they have a different electronic properties that need to be one have to consider. So MOF with open metals site can be provide a preferential binding site for this molecule and maybe allowing a preferential adsorption of H2 compared to others. And that's where we can also separate them. And this enables a single step purification process that replaces a multi-stage conventional system. And there are many separation process like breakthrough separations, where it's the kinetic separation rather than equilibrium separations. And MOF with the precise pore aperture can discriminate based on the molecular diffusion rate. And H2 diffuses rapidly, while larger molecules are sterically hindered. And but we have to think this is a classical separations when we talk about separation based on nuclear quantum, then this effects goes differently. So we have to think in that way as well. However, this create coming to the point. So this create a continuous separation process compatible with industrial hydrogen production timeline.
Right. So, um, can we discuss about hydrogen storage and how it presents different challenges? So, my question would be, how do MOFs compare to competing storage technologies, and what are the engineering trade-offs?
For the MOF hydrogen storage operate through physics option. Usually, it's a weak van der Waal interactions and that enable a reversible loading and unloading at the relatively mild conditions. And this contrast with the metal hydrides that really require high temperature for hydrogen release or a compressed gas storage that require high pressure infrastructure. That is where the metal hydrides works. So there's a two fundamentals mechanism that is involving. For the normal MOF based storage, it's only a physics option where the weak interactions are there. So it's easier to absorb and remove. But however, in the case of metal hydrides, they are hard because they are chemijobs, that is a very strong covalent bond interaction between H2 and the metal hydrides, which need really high temperature or pressure to load and unload these gases. And the challenges is achieving DOE volumetric target of so DOE is a um, so they set a target for how much amount of hydrogen should be uh, economical to be technically safe. So volumetric storage in a material. So it's called 40. So it's around 40 gram of H2 per liter by 2025. Even as a high surface area MOF struggles to meet target at the practical operating conditions and temperatures. And cryogenic operation, there's another methods. It's this is the cryogenic operations improve the capacity, but add system complexity, and it's need very low temperatures and energy penalties, and that trade off between the material performance and the system level efficiency.
Right. Let's discuss what engineering approaches do you think are improving volumetric performances?
So there are several strategies, which shows a very promising. So I think there's called a supramolecular crystal design, enabling this precise molecular packing using multivariant hydrogen bond, also called HOP systems, while which enhance the volumetric density without compromising the gravimetric capacity. So this kind of systems called HOF, hydrogen bonded organic frameworks, assembled via point contact nodal linkage, achieve up to 53.7 gram per liter volumetric capacity under the dynamic thermopressure cycling. That's what we are earlier discussed. So by 2025 it need to be 40, but this material has already exceeding. Another technique that or the not the technique, but the strategy that I think is geometric tuning of metal sides, such or maybe making some under coordinated side or open metal sides, especially copper system, which is known to show a really strong interaction between this H2 small gases through this Kupias type interactions, and which will increase the local hydrogen absorption density at near ambient conditions. Um, there are several also which like a polycatenation strategies interlock multiple frameworks to densify the structure while preserving accessible porosity. There's another hybrid material with material nanoparticles, which are known in materials where they use these spillover mechanisms using nanoparticles inside, but this is still in literature or academics only. And maybe this also one of the important, I think, the hierarchical pore structures, which combine both micropores for high surface area with mesopores for rapid diffusion and optimizing both packing efficiency and kinetics.
Right. Coming into the topic of stability and regeneration challenges, what I want to ask is that industrial implementation, as we might know, requires long term stability under operating conditions. How do MOFs address stability challenges in industrial environments?
So I think this is a very important question as well. So stability represents the most critical barrier to the industrial adoption. Many high-performance MOFs degrade in presence of water vapor, acidic conditions, or acidic gases, or some corrosive gases, or the mechanical stress. And condition in the which is usually present in the industrial process. And this fundamental issues is that the MOF crystallinity essential for performance and create inherent fragility. However, many stability, many stable MOF can be designed through rational design, or also call it the very famous researcher from this field is Omar Yagi, call it reticular chemistry design based on that. And yeah, I think there are many stable MOFs based on like zirconium based MOF. They are quite stable. Aluminium based MOFs, which are also very stable. And also, what I also already mentioned you about the Cal 20 MOF, which is also very stable, and it's already been in process for the using for separations and other applications. Especially, I think many structures have also this defect tolerance structures. And I think the hydrophobic functionalization can prevent the water-induced degradation. Some approaches utilizes hierarchical structure where the stable framework protects active site for environmental degradations. Yeah.
Right. So, what about the regeneration and life cycle considerations?
Regeneration efficiency directly impact the operating economics. MOF must maintain the performance through a thousands of absorption and desorption cycles without structural degradation or capacity loss. This is very important. And this require an understanding how repeated gas loading affect the framework flexibility, if there is any. So if there is like aluminum based MOF like MIL 53s, which is very famous MOF, which is very stable as well, and they have these flexibilities. So S-type hysteresis in their chops and isotherms. Also, with time, there might be a possibility of formation of defects into the structures, and also one can also think about how this accessibility of pores can be after 1,000 cycles. And so this advanced MOF incorporate the self-healing mechanism or defect tolerance structure that maintain the performance despite the minor structures. And there are some MOFs, yeah, which have this properties where they are very tolerant to this condition where they don't degrade. Yeah.
Right. So, as we conclude, what do you see as the most realistic timeline for widespread industrial morph adoption?
Mm, yeah. So we are likely 5 to 7 years from the significant industrial deployment, with niche application emerging sooner. High value separation like xenon recovery, rare gas purification may justify more cost in the near term. Broader application await further cost reduction and the stability performance. So the German industrial landscape, particularly in Mittelstand company, present a unique opportunities. And this, however, not only German but also in Switzerland and also in Canada, these companies are been emerging. And yeah, I think, and this medium-sized enterprises often have the flexibility to adopt the innovative technologies more rapidly than the already well set up multinational corporations, which have a sufficient technical sophistication to implement the advanced material solutions. Yeah.
Okay. And what do you think will be the factors that determine a successful market penetration?
I think the success depends on achieving three simultaneous objectives: performance that significantly succeed the incumbent technologies, manufacturing cost, approaching the conventional adsorbent, and the stability matching the industrial process requirement, as well as to have to just replace the material with already existing systems. And this requires moving beyond proof of concept demonstration toward the systematic engineering optimization. The most promising part involved MOF modular MOF platforms that can be adopted for different application rather than bespoke material for each use case. Standard synthetics protocol, commodity chemical linkers, and scalable processing equipment will ultimately determine commercial viability. Yeah.
Right. Okay. So, do you still have any final thoughts on the future of MOFs or MOFs and sustainable energy applications?
Well, MOF represent a rare opportunity to achieve step change improvement in the gas separation and the storage efficiency. Critical technologies for hydrogen economy, implementation, and carbon capture deployment. Success requires sustained collaboration between academic researchers, developing a fundamental understanding, and the industrial partner providing real world constraint and validations. And the materials are ready. The engineering implementation is the next frontier, what I really believe. Yeah.
Right. Thank you so much, Dr. Chetri, for this insightful analysis of MOF commercialization challenges and opportunities in sustainable energy applications. Thank you.
Yeah, you're welcome.